everyone. Welcome to the fourth lesson of the second term. So today we're going to consider work, energy, and power, but our focus is going to be on work. Work, energy, and power. Work. Let's consider the definition of work. Work is denoted by W. It is measured in joules. It is a scalar quantity. It is positive when the energy is transferred into the system. And it is negative when the energy is transferred out of the system. What is work? Work done on an object by a force is defined as the product of the magnitude of the force, the magnitude of displacement, and the cosine of the angle between the direction of the force and the direction of the displacement. It is the amount of energy that is transferred. This is the formula that we use mathematically to calculate for work, which is the force, delta x cos theta, where F stands for the force, delta x the displacement, the angle is the angle between the force and the displacement. So if the force is acting horizontal in the direction of the displacement, then theta is 0. If the force is acting at an angle, then we have F cos theta. Let's consider the first example here. Steve tries to impress Elaine with his new car, but the engine dies in the middle of an intersection. While Elaine stares in a straight line, Steve pushes the car 19 meters to clear the intersection. If he pushes in the direction of motion with a constant force of 210 meters, calculate how much work does he do on the car. Let's consider the solutions together. So we're given the displacement, which is 19 meters. The force is 210 newtons. The angle is 0 because the direction of the force and displacement is the same. Then we substitute to the formula. Then we get 3,990 joules. Let's consider the second example. Calculate the amount of work done by Steve. In the previous example, if the angle between the direction of his force on the car and the direction of motion is 20 degrees. So which means now Steve is pushing the car at an angle of 20 degrees above the ground. Okay, as follows. So we have the angle now, theta, which is 20 degrees between the displacement and the force. Then we substitute. Now we get the work, which is 3,749.37 joules. Okay, let's consider these important aspects about the work. So work is a scalar quantity, which means we focus on the magnitude only, no direction. Scalars can be positive, can be 0 and negative. So we should be careful. Scalars are not always positive. Just like a temperature, we do have a negative temperature. We also have a work done which is negative when it is done by a frictional force, which means when the energy is transferred out of the system. Work is always done by a force acting on an object. The force is acting parallel to the displacement, or the force has a complement that is acting parallel to the displacement, or parallel to the direction of the displacement. The object must be moving. To calculate work done by several forces acting on the same object, we have two methods that are available. For example, you can calculate the work that is done by individual forces. Then you add, to get work net, you add those work done by the several forces. Or you can calculate the net force, then you substitute it to the formula W equal to F delta X cos theta. Then now the force will be F net. Let's consider example number 3. A book is pushed 1,5 meters along a horizontal tabletop by a horizontal force of 2 newtons. The opposing force of friction is 0,4 newtons. Then number 1, we must calculate the work done on the book by the 2 newton force. Number 2, we need to calculate the work done on the book by the frictional force. Number 3, we need to calculate the net work done on the book by the above mentioned 2 forces. Then number 4, is any work done by the normal force on the book and the weight of the book? You must explain. Let's consider solutions. We draw free body diagram. That is a free body diagram. Then solution number 1. So we have work, which is the product of the force, displacement, and cos of theta. Then we make substitutions, then we get 3 joules. That is question number 1. Question number 2, we need to calculate the work done on the book by the frictional force. Let's consider the solutions. The formula is W equal to the frictional force times the displacement traveled by the object, then cos of theta. Frictional force is 0,4, the displacement is 1,5, and the angle between the friction and displacement is 180 degrees, because the displacement is forward but the frictional force is in the opposite direction, so the angle is 180 degrees. Then we get negative 0,6 joules. So the work here is negative because the energy is transferred out of the system. Number 3, we need to calculate the net work done on the book by the above mentioned 2 forces. Okay, so what we can do, we can calculate the net work, the net force, or we can calculate the work net, which is the work done by the applied force plus the work done by the friction. So then we combine, we get 2,4 joules. Or we can calculate the F net, which is the force plus friction, which is 2 minus 0,4, which is 1,6. Then after that, we substitute it into F net. Then we substitute the displacement, which is 1,5. Then we substitute the angle, which is 0. F net now is forward, which is in the direction of the displacement. Then we get 2,4 joules. Or we can say F net is applied force minus friction, which is 2 minus 0,4. But the best is to substitute the negative when you make substitution. Just say F net equal to F plus friction. Example number 3, question 4. Is any work done by the normal force on the book and the weight on the book? You need to explain that. So the normal force is acting perpendicular to the displacement. And also the weight of the object or gravity is acting also perpendicular to the displacement. Then which means there is no work done, because both the normal force and the weight are acting perpendicular to the displacement. Or we can say cos of 90 degrees is 0. Let's consider the work that is done by several forces. So we have work that is done by the applied force, which is W equal to applied force times displacement cos of theta, where theta is the angle between the applied force and the displacement. We have the work that is done by gravity, which is work equal to mg h cos theta. The force is the same as mg, which is gravity. The displacement is the same as the height. Then theta is the angle between gravity and the height. The work done by T, which is the tension, is the work equal to tension times displacement cos of theta, where theta is the angle between the tension and the displacement. We have the work done by the net force, which is work equal to net force times this displacement cos of theta. We have the work done by the conservative force. We have the work done by non-conservative force, which is work done by non-conservative force, which is equal to change in mechanical energy, which is change in kinetic energy plus change in potential energy. We have the work done by friction, which is W equal to a friction times displacement cos of theta, where theta is the angle between friction and the displacement. Work energy theorem. The net work done on an object by a net force is equal to the change in kinetic energy. That's how we state work energy theorem. Work net is change in kinetic energy, which is half mv final squared minus half mv initial squared. Work net is positive when the object is speeding up, and it is negative when the object is slowing down. Let's consider example number 4. A little wagon with a mass of 2.5 kg moves in a straight line on a frictionless horizontal surface. It has an initial speed of 3 meters per second, and then pushed 4 meters by a force with a magnitude of 2.5 newtons in the direction of the initial velocity. We need to calculate the wagon's final speed. Let's consider the free body diagram. We have the normal force acting upwards. We have the applied force of 2.5, which is acting forward. Then we have gravity, the weight which is acting downwards. So we're given the mass, which is 2.5 kg, the initial velocity of 3 meters per second, displacement of 4 meters, and an applied force of 2.5. Then we use work net equal to change in kinetic energy. Then we substitute F net there. Frictionless surface, which means F net is the same as the applied force. Then we put 2.5, displacement is 4. The angle between F net and the displacement is 0. The mass is 2.5. The final velocity is what we are looking for. The initial velocity is 3 squared. Then we make V final the subject of the formula. We take this term to the other side. Then after that, we multiply both sides by 2 and divide by 2.5. Then we get 4.12 meters per second. That is the final speed. Okay, learners activity 1. You need to do this by yourself at home. A ball with a mass of 0.145 kg is thrown straight upwards with an initial speed of 27 meters per second. If air resistance is ignored, calculate the amount of work done by gravity on the ball when it reaches a height of 20 meters. 1.2, we need to calculate the speed of the ball at a height of 20 meters. You need to use only the work energy theorem. Example number 5, an object with a weight of 20 newtons is sliding from the top to the bottom of a frictionless inclined plane with a length of 10 meters. The angle between the inclined plane and the horizontal is 30 degrees. Calculate the amount of work done on the object by its weight. Okay. Let's consider the first diagram. This is in an inclined plane. So we have the normal force, which is always acting perpendicular to the inclined plane. Gravity always acting downwards. Then the angle of displacement, which is down the plane. And we also have a height there denoted by delta y. So the first method, we say the work done by gravity is W times the height cos of theta. So W is acting downwards, the height is also acting downwards, which means the angle is 0. Then we get 100 joules. Number 2, so we can calculate the work done by a parallel component of weight. So the W parallel For the component of the weight, parallel is 20 sine 30, because this component, which is responsible for the sliding down of an object, it is opposite to 30. That's why we have mg sine 30. And remember, this angle is always the same as the angle of the plane, because if you close the plane, this will close also. The normal force will go straight up, then this will come to W, then, which means this angle is 30 when the angle of the inclined plane is 8. Then we calculate here the work done by the parallel component, which is also the same as 100 joules. Why is it the same? Because the work done by conservative force is independent of the path taken. That's why you get the same answer whether we use the displacement or we use the height. Just like the work, if you are using a lift or you are using the stairs or you jump, the work done by gravity will be the same because it is independent of the path that is taken. Let's consider example number 6. The diagram below shows a track ABC. The surface AB is frictionless. The rough horizontal section BC is 8 meters long. Calculate the frictional force exerted on the object as it moves along BC using energy principles only. Okay, let's do this together. Let's check what we have. So the object comes to rest at C. So we have the displacement here, which is 8 meters. So what we need to do now, we need to calculate the speed here at B. Example number 6. So we use work energy theorem. Work net is equal to change in mechanical energy, which is change in EK plus change in EP. This is the same as half mv final squared minus half mv initial squared plus mgh final minus mgh initial. Okay, so we're given the mass of the object, which is 10 kg. Okay, so let's take the mass here. Okay, it's not indicated there, is 10. It is 10 kg. So the mass is 10 kg. So the mass there is 10 kg. What else is given? So initial velocity at A is 0. Okay, let's check. The height is 4. Height final is 4 meters. No, this is height initial, and the height final is 0 at B. So what we don't know is V final. So let's calculate V final. Can say EM initial. is equal to EM final, which means mechanical energy initial equal to mechanical energy final. We have mv initial squared plus mgh initial equal to half mv final squared plus mgh final. Then you can substitute. Kinetic energy initially is 0. So the mass is 10, g is 9,8, the initial height is 4. The mass is 10, v final is what we're looking for, plus the height is 0 on the ground. Then we can make v the subject of the formula. We're going to have v equal to the square root of 10 times 9,8 times 4. It's going to be all over 5. Okay, let's get what is the answer. The square root of 10 times 9,8 times 4 all over 5, which is equal to, the answer here for the velocity is 8,85 meters per second. Okay, that is the speed at the bottom at point B. So now we can be able to substitute to get the frictional force. Okay, we can use now the work energy theorem, which is work net equal to half mv final squared minus half mv initial squared plus mg h final minus mgh initial. Okay, so the work net is also the same. Okay, let's use, it's also the same as the work that is done by non-conservative force. Okay, so the work done by non-conservative force is the same as the friction times the displacement, then cos of theta. So which is the same as half mv final squared minus half mv initial squared. Then the change in potential energy is 0 because the plane BC is horizontal. Then we have F times the displacement, which is 8 cos of 180 degrees, which is equal to half. The mass is 10. The final velocity is 0 minus half times 10 times the initial velocity is 8,85. Then we square. Then we make the F the subject of the formula by dividing by 8 cos 180 both sides, which is 48,95 newtons. Okay, that is friction. So here friction we can calculate it by using the work done by the net force, which is change in kinetic energy, or by using the work done by non-conservative force, which is change in mechanical energy. Okay, let's go back to our notes. Okay, learners activity number 2. We say a box is held stationary at point A, which is the top of a plane ABC. inclined at an angle to the horizontal. The portion AB of the plane is smooth, while the portion BC is rough. Okay, you can see there, AB is smooth and BC is rough. So 2.1, you have to state the principle of conservation of energy in weights. 2.2, calculate the speed of the box at point B. Then 2.3, the box experiences a kinetic frictional force of 14.7 newtons as it moves with a constant velocity from B to C down the plane. Then 2.3.1, you have to state the work energy theorem in weights. 2.3.2, you need to draw a free body diagram showing all the forces acting on the bob at B. Then 2.33, use work energy principle to calculate the distance D between B and C if the box has a mass of 3 kg. So 2.3.2, you draw a free body diagram showing all the forces acting on the box at B. Okay, that is the end of the lesson. Thanks for taking part in the lesson. Learn, grow, and succeed. Okay, thank you.